Yes, exactly. I realized that in the recordings you can't hear the people talking, and I had that like for the first couple recordings it was working, and for the past many, it hasn't, and I don't really know why. Let me see here quickly if I can just quickly do it.
Oh, by the way, I think you're the reason I'm passing linear algebra, like the second attempt.
Well, I'm happy to help. Okay, I think actually now it's gonna work. If someone says something, can someone say something? Okay, I saw the level go up, so hopefully they're not louder than me. I'm gonna just like turn it to probably hopefully. Okay, that should be good now. I don't know. It should really test this before, but okay, now I think that you'll be able to hear people in the thing, so I think it's gonna be good. Let me open up the textbook and let's just do a quick, thorough section by section, just kind of what's everything we need to know and all that, right? So I think it starts with it's not 6.3, 5.3.
Wasn't it 4.1?
Well, but
4.1 to 4.3,
but
isn't it?
but in kind of more the order that we did everything in. It starts.
True, yeah.
We finished the end of the last test was 5.2, then it was the rest of 5, and then it was chapter 4, and then chapter 6. So I think I'll do it in that same order because I think that's a good order to do it in. Okay. So, okay, well, let's just start. So 5.3 is called I should really type it, but okay, I guess I probably will just type it. Is just the fundamental theorem of calculus. And I'll just write it all out here. And I think I'll just do, probably people have seen it, but let's do just a couple of stuff here. So there's two parts to it. The first part is, the first part in general is if I have a curve, right? If I just have any curve, and I call that my y-axis, and this my x-axis.
I'm paying for it.
Oh, someone's paying for something. Someone has their mic on. Okay, I think we're good. So if I define a function, I say, well, let's just call this x, and I want the area under the curve between 0 and x. Let's just call that function capital F of x for no reason. Well, the fundamental theorem of calculus is saying that the derivative.
Wait,
oh, someone's got their mic
at
on.
like another place. They're not at the cash.
It's Colin.
I guess I'm not thinking, but it's like.
Who is it here?
It's Colin.
Colin? Yeah. Colin, you got your mic on. Colin, you got your mic on.
He's out paying for it.
Now he's off.
Someone great. Muted him. Thank you, whoever muted him. Okay, great. So, again, if I define just some function that is the area under the curve between 0 and the x value, well, the fundamental theorem of calculus is saying that the derivative of that is the function. Okay, that's what part 1 is saying. So the rate of change, the instantaneous rate of change of that function that gives me this area is just the actual f of x itself. And so in more concrete terms, it's saying that f of x, or first of all, the big F of x is equal to the integral from 0 to x of f of t dt, right? So it's a function that, I guess this is really your t-axis, right? This is really your t-axis. And so the area under the function between definite integral between 0 and that x value is what this function is defined as. And the fundamental theorem of calculus is saying that the derivative of that function is just f of x. Okay? And so that's the first part. Okay, which kind of makes sense. I think it makes sense. If you think about like how, if you were to slightly nudge this, right, you'd have that. The rate of change of that slight nudge would be related to the actual function itself, how the function is curving at that point, right? And of course, this also generalizes to just a at the bottom, right? It generalizes just between, this doesn't have to be your x-axis. So just between the point A and x, well, it's just f of x from, it's just, yeah, the rate of change of that is just f of x. And so the second part of the fundamental theorem of calculus is saying, well, if I want to actually calculate this area, and so maybe I'll draw another picture. If I want to actually calculate this area, so like this, right? And specifically, I want to calculate the area here, between here and here, right? Between A and B. So I'm trying to calculate the definite integral from A to B of f of x. Well, dx. Oops, did I not write dx is up here? No, I wrote dx. Okay. Well, all I need to do is, well, use that function that I defined before. This capital F of x is the area from this point. Let's call that 0. So from that point, boom, that's 0 to definite integral from 0 to x, right, of f of t dt. So again, this is your kind of your t-axis. And so to figure out what this area is in here, this middle bit, right, this section, well, I just take the area from here to here, right? In other words, capital F of B, right? And I subtract the area from here to here, capital F of A. And that's going to be my area. That's going to be the integral of f of x dx from A to B, right? And so we can put these two things together, right? We can say that actually the way to find capital F of x, because right now we don't really have a way to find capital F of x, but the first part is kind of telling us that. It's saying that if we want to find what capital F of x is, well, we just need to find, got to find the thing that its derivative is f of x, and then we can use it just like this. All right, so that's this is what part 1 is saying. And this is what part 2 is saying. Like that. Okay. And that's very useful, obviously, right? That's, it just is. Let's do a couple examples. Maybe one where it's a little more complicated. Okay. Let's do a quick example of using, and I'll definitely, I think, go for the hardest example from each section. Although I don't quite, oh yeah, I see. Okay, I'll try to combine two examples. Can I combine this example? Okay. Yeah, I think I'll do this. So let's say that I should use a different color. Let's say that capital F of x equals the integral from x to x squared of cos t dt. Okay, and we're looking for f prime of we're looking for capital F prime of x. Okay. Well, okay. So I'm kind of skipping a few examples here, so we're gonna go a little forward, but this is kind of, we can split this integral up into from x, the integral from x to, oops. Oh, hold on. Let me make sure I do this right. I'm trying to copy not the example, but the one from before, but now let me just make sure. Both of these been two integrals. Yeah, okay. So we split this into two integrals. We can split it between x and 0 of cos t dt plus 0 to x squared of cos t dt. And then flip this one here, right? So this is like this. So it's going to be from 0 to x, negative 0 to x of cos t dt, right? Plus 0 to x squared of cos t dt. So now let's try to find, so this is big F of x, right? This is capital F of x. And the reason I did this is because now I can just take the derivative of each of these things separately. Okay, so the derivative big F prime of x, well, the derivative of this, based on what the fundamental theorem of calculus says, is that if it's just from 0 to x, right, this is just equal, and for the sake of writing it all out, I'm actually going to write this as, this is negative f of big F of x, and I'll put a prime like that. Okay, negative big F of x plus big F of x squared, right? Prime. both of these prime. So I'm going to actually take the derivative now. Well, the fundamental theorem of calculus says that this derivative here is just cos x, right? Is just cos x. And this one's a little bit more complicated, right? So this one is going to be plus, it's f of x squared. So it's a composite function here, right? We're doing f of g of x. So we got to use the chain rule. So the derivative of this is the derivative of the outside, right? The derivative of the outside is cos of x squared. And then you got to multiply it by the inside, 2x. That's just the chain rule, right? Multiply by the derivative of the inside function. And that should be your answer. I don't know what the answer isn't written here, but that should be the answer. Right? That's f prime of x. And I think writing it out like this is an important step, right? Because you're saying that this is big F of x, because that's the thing in the top there. This is big F of x squared. That's the thing you got to notice, right? And when you have both of the bounds as variables, then you got to break it up into something like this. Right? And I'm pretty sure you could have chosen any number for E0 here. I don't think it had to be any number for the lower bound. I don't think it had to be 0, although I could be wrong about that. But I'm kind of just following this example. But yeah. So anybody stop me if they have questions and they are confused or don't know what I'm saying. But yeah.
Didn't you use 0 because it's like easier to cancel out and like it just leave you with the variable whatever thing?
I think it would work the same though, because the theorem is from a to x, right? So any value a to x.
Yeah, but then you'd have like cos 1. Oh, wait, yeah.
I'm not actually evaluating, right? I'm not actually evaluating. I'm just okay. Defining that. So okay, so anyways, there's f prime of x. Big F prime of x. Okay. Then, let's see, what else is there in this? I'm just scrolling through the may as well put on the screen while I'm scrolling through. So, yeah, that looks like it. So, does anybody, I guess I should have said before, but does anybody have any particular questions they want me to do from any of these sections? I guess maybe prepare for further sections too if you think like, oh, there's one from 5.7 or something like that you want me to do. Or whatever, 4 point something. So, yeah, but anyway, anything from 5.3. Preferably anything that was on the homework, because that's what I did, and that's what I probably know how to do, but I'm happy to do whatever. Okay, then I'll just keep going. Okay, I kind of want to try this one because I just like the picture, so, but I'm not going to do it now, but I like to try it. Okay, integration formulas and the net change theorem. I don't quite remember what this was. Oh, this was just a basic integration, I'm pretty sure. The new value of changing quantity equals the initial value plus the integral of the rate of change. Plus the function of a. Yeah, it doesn't look. Oh, actually, we think we skipped this, didn't we? No, 4.4 we skipped. Never mind, that's not true. 4.4 we skipped, not 5.4. So, is that true? Yeah, 4.4 we did skip. Okay, never mind. So, what is this doing? Let's see what. Oh, I went to the wrong section, of course. What's the question here? Use the power rule to integrate that. Find the definite integral. Okay, it looks like it's just basic integration. Apply the net change, given that velocity for particle motion times c times 2. Let's see what my notes have in my book for it. Let's see if there's anything interesting there. And see what they say. Yeah, it was pretty short. So, yeah, nothing much really from here. Honestly, I think I even remember doing the homework and it was literally just, I couldn't really even tell you what this section was about. It's just.
Yeah, wasn't this about like the fact that it's f of b minus f of a as a definite integral, and then you use that as area or whatever?
Yeah, that's what you're doing. That's what you're doing throughout the whole thing. Just like, it also introduces sorry, you go ahead.
No, it's fine.
I was just going to say it introduces that if you have an odd function evaluated from negative a to a, the integral of an odd function evaluated from -8 to a, that's always 0. And an even function is a little less useful, but there's also a formula for that. I guess I'll write it down.
Right. Yeah.
I think it might even be here. Here. There you go. Those are the two formulas. And that's all I can say really about 5.4. I really don't know what else to say. Yeah. So I guess I'll move on unless anyone has any questions. The next section would be U-Substitution. So I will just pull that here. U-Substitution. So 5.5, and I'll write the section header. U-sub is basically if you, right, so our capital F of X, is the antiderivative, right? Is the antiderivative. So we get this, we use this when the thing inside the integral is the result of taking the derivative, right, of something that's a chain rule problem, right? So like f of g of x, right? So in general, right, f of g of x prime, the whole thing prime, is equal to f prime of g of x times g prime of x, right? And we're looking for that form inside the integral. We're looking for that form inside the integral, and that's when it's useful. That's because when you have a composite function thing, and you have very often composite function things, right? So I guess let's start with an example. I probably will do a couple examples here, just in case people have trouble. Let's see. Okay, here. Well, okay, let's do a simple example first, and then if people want me to do harder ones, I'll do harder ones. So the integral of 6x, 3x squared plus 4 to the power of 4 dx. So I'm pretty much, this is what this is asking is just find the antiderivative. Find the antiderivative, okay? So in other words, the antiderivative, right, if we're going backwards here, we're looking for something that's f of g of x, right? We're looking for that because the derivative of that will be this function. That's what the whole thing is, right? So, well, usually the best thing to do is just say the thing inside your bracket is your u. So u equals 3x squared plus 4, right? And then what you do is you take the derivative with respect to x, right? Du dx is equal to 6x, that's it, just 6x, right? And so the trick is the thing that we're doing any different here is we just move that dx over, right? So it's du equals 6x dx. Now, that's treating it like a fraction. Du dx is not a fraction, but it definitely can be treated like a fraction sometimes when it's useful. So I don't know the rules on that any better than you, I think. It's just like du dx looks like a fraction, written like a fraction. You can't treat it like a fraction except when it's useful, and then you can. So this is one of those cases. You can treat it, you can use it like a fraction. So we just multiply both sides by dx, and we just have du equals that. Well, notice here I can rewrite this, right? Multiplication goes both ways. So to the 4, this is 6x dx. So I'm saying u equals 6x dx. Okay, well, I can just rewrite this as, and u is that thing on the inside, so it's u to the power of 4 du, because du is 6x dx. Okay, well, this is a lot easier to integrate now. I just use the power rule, right? So it's going to be u to the power of 5 over 5 plus c. And I just got to remember to put the u back in. I always forget to do that. So 3x squared plus 4 to the power of 5 over 5 plus c. And that's your antiderivative. So if you were to take the derivative of this, right, try to imagine bringing the exponent down, it cancels out, and then you have there'll be a 4 up there, and then the derivative of that is just 6x. So the derivative of this would be our integrand here, and so that's the antiderivative. Okay, let's see another one. Does anyone have a particular U-sub question they want me to do? I think I'll do a trig one next, unless anyone has any suggestions. So the next one I'll do is this trig one. So it's sine t over cos cubed t dt. So I'll choose my u to equal sine t. Might not work. I guess it's probably actually... no, it's probably better to choose it to be cos. So cos t. Okay. But actually, for the sake of argument, let's just see what happens when I choose sine. Okay, so then let's see why it doesn't work. So if I take the derivative with respect to t, I get not negative, I just get cos t. So du equals cos t dt, right? So, well, what needs to happen is that when I do all this, I need to be able to replace every t containing thing in that integrand. I need to replace everything with something containing u. It can't be half and half. You got to have either everything be t or everything be u. So, okay, well, the top is now a u because u equals sine t dt, or u equals sine t. But I can't do anything with the bottom, right? I can say cos cubed t, and then, well, I want to replace dt as well, so I can maybe move that cos t over. So du over cos t equals dt. So I could put a du over cos t. But now all I have is u over cos to the power of 4t du. And I still have a t there. So that substitution didn't work. And that's how you can tell, because there's no way that you can get everything in here to be u, right? So it didn't work. Not a good thing. So in general, I think now I don't know how useful it is, but I just kind of think, well, first I'll just do the thing that's having the most things applied to it, right? So the thing inside, I can't spell, brackets, or with an exponent, right? And then I was going to say the thing that has the derivative that's also in there. But in this case, it's both of them. So in the last example, this was my u because its derivative is also in here. So that's a good choice for u. But in this case, it doesn't really count because sine t, okay, sine t, its derivative is cos. Cos, its derivative is sine. So it didn't really help. So,
yeah, so what would be the more complicated function, most of the time?
Sorry, what'd you say?
Would it be the most complicated function in the integral?
Well, it would be
would
a part of it. Would it be the most, what does it mean most complicated? Inside brackets with exponents?
So, yeah, exactly what you're talking about. It's the one that has more exponents, as you listed, inside brackets, more exponents. So anything that you find complicated or that's in the, denominator, you usually use as your u, but it can vary for some situations.
Yeah, so that's not a set rule. Yeah, I guess the denominator is also a good idea because you're gonna be multiplying at the top here, right? Because it's the dt is in the numerator, so that's gonna deal with the stuff in the numerator. So I guess denominator, but that's again, it's not a very set rule. It's sort of just gotta see what's going on.
Mm-hmm. All right, thanks.
No problem. So I'm gonna say u equals cos t. Okay, I'll make that clear. That's a t. U equals cos t. So du by dt is equal to negative sine t. Okay, and what I'm going to do is I'm going to multiply both sides by dt. So du equals negative sine t dt. And look at this. Well, I can move this negative sign over here, right? Move that over. And look, sine t dt, we have that. Oh, that's good. So negative du is equal to that. So here, negative du is equal to that stuff. And all that's left, so this should be really multiplied, is 1 over u cubed. Well, that was a successful u-sub, because now everything's replaced with a u in here. So I can move that negative to the front, and it's just 1 over, actually, in fact, I'll just say u to the negative 3 du. And now I can just integrate this with a equal sign, with just the power rule. Right, so it's going to be negative u to the power of negative 2 all over negative 2 plus c. Well, sorry, I guess I don't even have to write that. So there, plus c. And I guess technically maybe if someone might be seeing this and saying, well, wasn't there brackets around here? So shouldn't this be negative u to the power of negative 2 over negative 2 minus c? Sure. This c is any number and no particular number. So we don't need to keep track of what that number is. It's not like a variable that represents a number. I mean, it does represent a number, but it represents a number, any number, and no particular number. Right? So
an arbitrary number, basically.
Yeah, right? I think exactly. That it's just like it doesn't at all matter what that number is. So that's why I say it like this. This is what made sense to me, is saying and no particular number, because it's like it doesn't matter. But yes, an arbitrary number. So I guess I can simplify this a little bit. This is going to be 1 over 2u squared plus c. And then that's the answer.
I remember my teacher saying how if you have like du over u, you have something like ln of the, it was like ln of the absolute value of u plus c. That's what my teacher did sometimes, because maybe it's like the 1 over u.
So yeah, you're saying 1 over u, but this is 1 over u cubed. Here you can use the power rule. But if you had the integral of 1 over x dx, right? You can't use the power rule, because, well, let's try. Let's see what happens if I use the power rule. It would be x to the negative 1 dx. Okay, so I would be saying, okay, raise the exponent by 1. It's x to the 0, and divide by the new exponent. Doesn't work. Plus c. Right? So you got to do something else here. So the power rule doesn't work here. And so the answer is that this is just equal to ln of absolute value of x plus c.
Okay, so because there's the it's cubed, you can't do that. The ln of
you can just do the power rule. You can just like would the ln thing work? I think the ln thing is only for if you have 1 over x, specifically 1 over x. Right? Not
okay,
for 1
so
over
in this
x
case
squared or cubed or anything like that. Just 1 over x.
It would just be du over u. Okay.
Well, it was u. Yeah. Okay. So yeah. So that's the answer. One thing I forgot, which I always forget, is to put the u back in. So u was cos t. So it's 1 over 2 cos squared t plus c. And that's the answer. I always just think I'm done when I do that. And then, yeah. Okay, so I do want to do one that has 2 u subs. So let's see. Oh, actually, I should do one with the definite integral too. And actually, I don't really like you don't have to worry that much about doing the definite integral. Like, it's how you do it. It's not actually any different. And I don't know. I don't particularly even like how it works, because I think it would make more sense if you just left the rules the same. But anyways, so it's slightly different if you have a definite integral. So let's say this one, the definite integral of x squared times 1 plus 2x cubed to the power of 5 dx. Okay, so, well, good thing to try is just say, well, u is our thing inside, so 1 plus 2x cubed du by dx is 6x squared. Okay, we have an x squared out there, so we can deal with the x squared. Right? I'm gonna flip these. What will I flip? Yeah, I'm gonna flip these around, right? Because we can just flip those around. So du over 6x squared equals dx. Right, just doing some algebra. So what I can say now, the reason this is useful is because look at this, right? I can say the integral of, now I'm going to say that's u to the power of 5, right? X squared, now I'm going to replace dx with du over 6x squared. Well, so you might be saying, well, we still got a x in there, but of course, the x's cancel. We can move the 1 over 6 to the front, and now we just have u to the power of 5 du, which is 1 over... Oh, and I've been messing up the definite integral things. Okay, so when I do the U-substitution, up here, you gotta evaluate U at that x value. So what is U at 1? So it's 1 plus 2, so it's just going to be a 3 up here now. And 1 plus 0 is just 1. So the limits of integration change. The reason you do this is because now, when you get to the end here, when you actually evaluate this integral, so it's still a 3 and a 1 there. So it's 1 over 6 times the integral of u to the power of 6 over 6. Well, no plus c because it's definite. Right? Evaluated from 1 to 3. Well, what you can do is you can just put in this value now. Instead of putting u back in. Now this is the confusing part, is you don't put u back in here. You don't say that. That's not the case. You can just use this value. Just use these numbers. If, for example, you forgot and you didn't change the limits of integration as you were going, the only difference is that you would then have to put u in and then just evaluate the x values. It's the exact same thing. So honestly, I would do it like this just because this is how we've been taught. But I think it makes more sense to just put the u in and then evaluate at these integrals, at these things.
You know, I thought I was going crazy when I was doing these and the answers weren't matching up because I kept on putting u into it before I put the 3.
Exactly. You don't so just for this, you don't put the u in. Right?
Because the textbook answers were completely off and I was getting frustrated.
Yeah.
Thank you.
Yeah. So that's what it is.
So definite integrals, you just like substitute the thing and
you actually substitute these values in without substituting the thing for u.
Okay. And then for indefinite, you just substitute u and then just use the
and then it's
integrals
done.
that they give.
Well,
okay.
for indefinite, there's no boundaries, there's no limits, right? So, yeah.
Okay.
So after that, right? After the point we have it at 1 over 6 and then u to the 6 over 6, right? Wouldn't it just become the FTC method where you plug in both top and lower and upper bound and subtract it from each other?
Yeah, exactly. What is capital F? Capital F of x is equal to 1/6 u to the 6 over 6. Right? That's capital F. So we just need to evaluate it at 3 and at 1 and subtract those two. Right? So I can factor out the 1.
Hey Adam, could you go up a little bit?
Yeah.
Just before you continue.
Yes.
Could you explain how you got 6? I'm kind of curious how you got 6x squared.
Here, this here? I took just took the derivative of this side.
Oh, okay.
Right? So power rule brings that down, and that's 6x squared. Good?
Wait, I forget. Where'd you get 3 again? I know you had to like change it somewhere.
Oh, this 3 here? This 3 here?
Yeah.
Yeah. So I'm just taking each of these limits. So this is our original x value. So I'll call this x2 and x1. So the new x2 and x1 and x2 is you evaluate u at that x value. So for the first one, that's equal to 3. So I evaluated this here, and that goes there. And similarly, I say u equals 1 plus 2 times 0 cubed, which is 1. And so that went there, so that went there.
Okay, yeah, that makes sense. That makes sense. Thank you.
No problem. Okay. And then, so just the last step is to actually do it, right? So don't put in the u from before. We just look at this. So we just say 3 to the power of 6 over 6 minus 1 to the power of 6 over 6. Yeah. So 1/6. Well, this is 3 to the power of 5 over 2 minus 1/6. And I don't know past that. I'll plug into my calculator, I guess. 1 over 6 times 3 to the power of 5 over 2 minus 1/6. So I got 182 over 9. Okay, so Oh, I guess I may as well do an exponent one as well. Like an exponential function one. Okay, let's do an exponential function one. So the exponential function one is a definite integral, so it's from 0 to 1 of x e to the 4x squared plus 3 dx. Okay, that's our integral. We're evaluating it from 0 to 1. So the thing that has the derivative in here, x's derivative is 1. So it's not really useful. There's a 1 in here, but it's not really useful. The derivative of this is that's in there, but it's multiplied by this, right? The derivative. So not really useful either. But this, the derivative of this is 8x. X to the power of 1 is in here. So it looks like the most useful thing to do is to say u equals 4x squared plus 3. So du by dx is equal to 8x. And so what I'm going to do is, notice here I can the reason I'm doing it is because notice here I can rearrange this to be e to the 4x squared plus 3 x dx. So I want to have an expression for x dx. So to do that, well, I would just say, can I do this? So du over 8 equals x dx. Pretty sure. Yep, that sounds right. So, well, look at that. X dx is du over 8 is equal to x dx. So I can rewrite this as, well, not that, but e to the u times du over 8. And I just got to adjust these limits of integration now. Okay, so when I take this top one, right? So u equals 4x squared plus 3 for 1 squared plus 3, which is 4 plus 3 is 7. Right, so that went there, that goes here, which is a 7. And then finally, but the second thing is 4 times the bottom limit was 0, right? Yeah. So 0 squared plus 3 equals 3. So this goes here, this goes here. So from 3 to 7. So the next thing we can do is just factor out that, well, not just factor out, but the scalar multiple out that 1 over 8. Okay, so the scalar multiple is out. And it's just a 3 to 7 of e to the u du. Well, of course, the antiderivative of e to the u is e to the u. That's what it means to be that exponential function. So we just have 1 over 8. Oops, didn't write the fraction line. 1 over 8 times the antiderivative of e to the u, which is e to the u, evaluated from 3 to 7. Again, don't put the u in. All we do here is we just say 1 over 8 times e to the 7 minus e to the 3. And that's the answer. You can leave it like that. Maybe if you want to write it like e to the 7 minus e to the 3 over 8, that works too. But there you go. Okay, so there was that. Again, if anyone has any questions, just stop me. Oh, I should have the chat open. So yeah, if you want to say something, go in discussions for MTH 140. Okay, someone asked, how did sine t become negative? But that was 10 minutes ago. If they want me to go back to it, then let me know in the chat.
Yeah, can we do a log function?
Yes, I think if there's an example in the book here. Yes, this is recorded, if someone was asking if this is recorded. Just making sure. Yes, it is recorded. Oh yeah, thank you, Vishal, for posting that. Let me find Trigonometric. There's a trig one, because I didn't find any log ones, but if you have like one from the book that I can do, and I'm thinking log ones, like which ones?
Wait, can you do example 5.46?
Sure.
From, I don't know, 5.6, yeah.
Oh, that's from the next section. Yeah, that's from the next section. Okay, yeah. Okay, so I'll move on to that. Yeah, just once. Like, is everybody good with 5.5 substitution? I didn't do a substitution with 2 substitutions in it. Would someone like me to do that?
Yeah, sure.
Then I just need to find the question. I don't know which question has the doubles, like 2 substitutions in it.
Yeah, it's alright.
If anybody knows one, let me know.
Wait, but how would 2 substitutions work? Because then you need 2 bounds. Because you're bounding by u, and if you use like w, you bound by w as well.
Well, you would replace it. So the bounds here, it's not like here the bounds aren't 0 to 1 and 3 to 7. You just replace 0 to 1 with 3 to 7. So you just replace it. You just replace it again.
I see. Makes sense.
Okay.
I'm pretty sure the past exam that's on D2L has a double substitution
Okay,
thing.
let's take a look.
Well, I have one from the lab. If you want me to send it to you, I can.
Sure. Yeah. Sure. You can send it, and I'll look here. Oh, that's not what I want. Yeah, someone can send it. I'll log in and see what we have here. Where am I? 140. So where am I going? Table of contents? Oh no, probably test. Oh yeah, we'll see. Test 3. Test 3. There. So this one has a double substitution thing?
Yeah.
Do you know which
I
question?
think, because I was struggling with it.
Let's see. Is it this one?
Yeah.
Okay, looks like that would be it, but let's just see what happens. So I'll separately do these questions. So we're not going to spend too much time doing the practice exam because I think I'll do them another time. But yeah, this does seem like it's going to be a good one. So our integral is from 0 to the cube root of pi of t squared cos squared t cubed times sine t cubed dt. So in general, the thing inside the bracket or inside the function is what I will make the u. So I'll say u equals t cubed. So du, or I'll say du by dt, is 3t squared. Well, luckily, t squared is here, right? So I want to get t squared dt. That's what I want because those things are together there, right? So I can just say du over 3 equals t squared dt. Okay, that's useful. So what I can do is I can say cos squared u sine u equals, not equals, but times du over 3. Okay, and I got to adjust these limits of integration. So if u is t cubed, then this is just going to be pi to 0. Because it's pi, it was cube root of pi, so put that in here. It's just pi. 0 cubed is 0. And then I can just move the 1/3 to the front. So it's the integral from 0 to pi of cos squared u sine u du. And yeah, so now I would say my next thing would be I'd say v equals cos u. And let's see what happens. Let's just see what happens. So dv by du equals negative sine u. My only thing is, shouldn't you take also the derivative of the view there? Chain rule. Let's see what happens if I don't. I think I don't because I adjusted the limits of integration. Maybe that's why we're supposed to do it, because then it lets you do double substitutions.
Yeah, I think you're right, because there's no way you could substitute the old one back in.
Yeah, right? So, okay, so then let's say dv, what am I looking for? So I want du sine u, right? Du sine u. So dv, negative dv, equals sine u du. Okay, notice there's our matching set, right? So this is going to be 1/3 Now I'm going to have to actually evaluate this. So v equals cos u, right? So cos of pi is 0, and cos of 0 is 1. So it's from 1 to 0. If they are backwards, it's okay. Why is it okay? Not quite sure, but that's what my teacher said. So, okay. So this is now just going to be v squared, and now sine u du is just negative dv. Right? So I can just say negative a third, right, from 1 to 0 of v squared dv. And now I can just do the power rule. Negative a third of v to the power of 3 over 3, evaluated from 1 to 0. So this would be equal to the upper limit, just 0. So it's just negative of the lower limit. So 1/3, 1/3. So.
Wait, how did you get 0 and 1 for the interval? Didn't we take, isn't v like cos?
Yeah, v is cos u, cos of the thing, right? So cosine of pi is 0, I think, right? Isn't that, maybe I'm wrong.
Oh yeah.
Negative 1.
Oh, cosine of pi is negative 1. Oh, okay, that's what I did wrong. Okay, never mind. So it's just a negative 1 up here, negative 1, negative 1, negative 1. So this is wrong. Yeah, cosine of pi over 2 is 0. Okay, that's what I was thinking. So we just evaluate at the upper limit, right? So it's just going to be, well, it's going to be a third. So I'll do it all full. I'll write it all fully. So negative a third, negative 1 cubed over 3, minus negative a third, 1 cubed over 3. Right? So this is just going to turn into a ninth, and this is just going to turn into a ninth. So that's going to be 2 ninths. And I think that's the answer.
Yeah, by the way, just something to add. Where you said up there that if the integral, like the definite part is flipped around, you could just flip it back around and put a negative in front. So like you can make it negative 1 to 1.
Yeah,
and then
you
negative.
could.
And it would cancel out the negatives.
Yeah, I guess then that would have done the job of this. That would have done the job of like what happened.
Yeah,
later
so
on.
eventually it happens anyway.
Yeah.
But yeah.
Makes sense. Makes sense. So there you go. There's the answer to that question. So. Okay, so let's get back to the textbook though. So that was nice. That was good practice. I just wanted to do a double substitution one. Let's take a look at 5.6 integrals involving exponential and logarithmic functions. So, well, we actually kind of already did one, but yeah. So if I have a function like the general rule of this, and I'll just write it here quickly. So 5.6 integrals of exponentials and how do you spell logarithms? Logarithms. Okay. Just want to not spell it wrong. So if we I think we already did an example like this, but let's do another. So let's do this one quickly. So the integral of x squared e to the negative 2x cubed dx. So we would just use a u sub here, but just the u sub would be in the exponent, right? So u equals negative 2x cubed. And now, so far I've been writing du by dx, right? But the how it's usually written is you just instantly multiply the other side by dx. Well, multiply both sides by dx. So it's just going to be negative 6x dx. So that's how I'm going to write it from now on. But if that's confusing you, then just write a dx here, and then without that there, and then multiply both sides by dx. So you get the dx like that. Okay, but this is how I'll write it now from now on. So negative 6x dx. Okay, so we want, negative 6x squared dx. Missed a square there. So we want x squared dx to be together. So I'm going to bring the negative 6 over. Right? Bring the negative 6 over. In fact, I'll just bring it there. And so then that's x squared dx. Great. So I can just write this as the integral of e to the u du over negative 6. Bring that negative 1/6 to the front, right? And so this is just equal to negative 1/6 e to the u plus c, which is equal to negative 1/6 e to the negative 2x cubed plus c. Okay. Let's try another one. I want to do like a harder one. If anybody has a harder question, I guess that's what the practice exam is, so maybe you shouldn't be expecting too hard ones from this, but the rules for this section, so there's a rules for the logarithm functions. I think I'll just write them down just so we have them. Is the integral of, well, so x to the negative 1 dx equals ln of the absolute value of x plus c. Then the integral of ln x dx, or sorry, ln x dx is equal to x, well, I guess I'll write like this. X ln x minus x plus c for some reason. I can't explain that one to you. Maybe if I just do the, yeah, actually, never mind. I can't explain that one to you. So the way I explain it is because the next one is just log base a of x dx is just equal to x over ln a times ln x minus 1 plus c. And so these are the same things. Just keep in mind that a is e, so then this cancels and that multiplies in. Now, why does this bottom thing work? I don't know. They also don't prove it here, so I can't explain it, but it does. So let's try a couple of them. Oh, they really don't do too many wild questions here. Yeah. So does anybody have any specific practice questions from 5.6 from the practice section? Okay.
Well, I'm looking at it, and like 286, I think, was like somewhere around that. That looked pretty hard.
Well, 286 is from the last section, but we can do that too.
Oh wait, that's the last section. My bad.
Yeah,
My bad.
Don't worry. Yeah, 286 does look hard. You're right. So we can try that because it looks like a hard one. But then, so while I'm doing that, if anyone wants to look in just the questions for 5.6 and see. So yeah, let's try 286. So that's the integral of, okay, let me write that a little nicer. The integral of cos theta minus 1 cos squared theta minus 2 cos theta cubed sine theta d theta. Okay. So
I think they want to see his identities.
yes, so I should.
Because I think I did this one actually. Wait, let me check.
Take some identities out here. Let's see what I have. Oh, here it is. So does anything look like that? Cos theta 2.
Yeah, I don't see any identities in this.
2 cos
Like we can
theta.
expand cos squared theta. Never mind.
No, what'd you say? Sorry.
No. I was just thinking we should expand cos squared theta, but I realized it
I
doesn't
don't
work.
know.
Maybe this is a double use up. Because there's no identities in this.
Yeah, it is substitution.
Well, it's
Pretty sure.
substitution. Ooh, I think I see something.
Don't we can't we factor like the cos out of that?
Yes, that's what we can do. So look at this. I think this will work. So if I say cos theta minus, oh no, never mind, that won't work. Okay, well yeah, we can factor out a cos theta, but it won't do what I thought it was gonna do. Cos theta, so it'll be cos theta minus 2 cubed. Oh, but do I have to cube this? Yes, I do.
Wait, we can just U sub cos theta in.
Yeah, I think I can just do that. Because what I was going to say is that, like, I thought two mistakes I made. I thought this was going to be power of 1. I would have put it in here. And I thought this would be cos squared theta minus 1. And then I could do something with the identity. But yeah, all of that was wrong completely. So let's just do a U sub. So
yeah, never mind. I did 87, not 86.
Yeah. Okay, I'll just try u equals sine theta. U equals cos theta. Cos theta. So du equals negative sine theta d theta. So helps us there a little bit.
Oh yeah, then that's it. I guess.
So it's just
Maybe
u
it's not as
minus
complicated
1
as it seems.
u squared minus 2u cubed negative out the front d theta. Because it's du, sorry.
Could multiply them and multiply apply the cubed.
The negatives in the front here. Put the negative in the front.
Oh, never mind.
Yeah. So I know that. So for people who are, if anyone's confused about U sub, I did a bunch of steps in one there, kind of, right? Just to make it a little faster, but I'll slow it down a little bit. This was negative sine theta d theta, and then just imagine what happens if I put, equals d theta. Imagine what happens if I put that there. Yeah. So now I guess I can just say.
You need a second sub.
Yeah, I just did a V sub.
For the cube.
You can just multiply them and then derivate.
No, but that's long.
Oh, there's. Yeah, I could definitely multiply them all together, but I don't want to do that. So.
Oh, you're looking for a shorter way?
Yeah, so let's. I can factor out a u. Yeah. What are you gonna say?
You can sub in v, and then you can solve the u minus 1 for v in terms of v.
That's true. We haven't done any of that yet. Yeah, that's true. So, then I'd have to say v equals u minus 1.
No, v equals u
squared minus 2u.
Yeah, and then you solve it in terms of v.
Yeah, that'll work.
It'll work.
Solve for u?
Solve for v in terms of u. Or sorry, solve
the double substitution thing.
So you see what you have right now. Change all the v, all the u's into v pretty much, and make it in terms of equal to u.
You don't need to do that.
Well, you do, because the u minus 1 wouldn't fit with a v cubed.
It does. So for dv, we got 2u minus 2. So if you factor 2 out, you got u minus.
Oh yeah. Okay, never mind.
Yeah, that makes sense. So this is a du here. So yeah, okay, I'll factor a 2 out of here. Yeah, okay, factor a 2 out of here. So dv equals 2u minus 1 du. So u minus 1 du is here. Yeah, okay, so this is just going to be 1/2 v cubed dv. Yep. And then we just use our power rule. So -1/2 v to the power of 4 over 4. Sorry, I'm writing it like I'm doing a definite integral. So just v to the power of 4 over 4 plus c. And then I'll just sub back in everything from back. So this will be, let me just simplify this a little bit. So this will be negative v to the power of 4 over 8 plus c. So now v was u squared minus 2u. So this is negative u squared minus 2u to the power of 4 over 8 plus c. And then here I said u equals cos theta. So I'm saying negative cos squared theta minus 2 cos theta to the power of 4 all over 8 plus c. And that's my answer. And yes.
I have a textbook question.
Sure.
Like another one.
From what section?
Wait, which one were we on? Like 5.6?
Yeah, either 5.5 or 5.6. You can whichever one.
Yeah, so I think it's 5.6. 353.
353. Yeah, that sounds like 5.6. 353 here. Okay, so in the following exercises, use appropriate substitutions to express the trigonometric integral in terms of compositions with logarithms. You said 353, right?
Yeah, 353.
Okay. So that's the integral of ln cosecant x cotan x dx. Oh boy. I don't know any of my trig derivatives, so I have to find them all in the book here. Okay. So no, that wouldn't work.
Can we make cosecant x du?
Let's try. Let's try. So u equals cosecant x, du equals
negative cosecant x cotangent x.
Yeah, and that's where we run into trouble.
I'd do it the other way.
Can divide by
Cotan x u, because the derivative of cotan x is cosecant negative cosecant square.
That'll be.
But can't you just divide by negative cosecant square like it's just a number?
Well, like in this situation here.
Like you can write du over negative du divided by cosecant x equals cotangent x dx. Wouldn't that work? And then you just put the...
That's correct, but I'll show you why that won't work. Cotan x dx. So what we have left is we have ln u, that's fine. And then here we have negative du cosecant x. But now there's no way for us to get rid of that x there on the bottom.
Can't we just put it over u?
I thought I could just write like 1 over.
Oh, could you write it over u?
Yeah,
that's possible. I never thought of that, but yeah, let's move the negative to the front and put a u there. Okay. Yeah, that looks all right.
Does anyone have an answer for this in case it's wrong?
Is this a number?
Check in the textbook.
53.
Yeah, there's one.
There's an answer in the back for this one. So.
Okay.
So, what would we use sub now? Oh no. We'd say v equals ln u. dv equals 1 over u du. Right. So this is negative integral of v dv.
Okay.
Right? So negative v squared over 2 plus c equals negative, v was ln u, so ln u squared over 2 plus c, and u was cosecant x. So negative ln cosecant x squared, should be another set of brackets there really, over 2 plus c. Okay, yeah, that worked. And I assume that's the answer. I mean, if someone could check, yeah, this one, maybe if someone could check it, that would be good. But, yeah. So, okay, any other things from chapter 5.6? Or 5.5?
Can you scroll up real quick? Sorry. I just want to see what I missed. Okay, so we just subbed in. for pod x. Okay, cool. Got it. Thanks.
Okay, no more, nothing else from 5.5, 5.6? If not, I'll just move on to 5.7. So 5.7 are integrals or antiderivatives. Well, I'll just do the actual title. Resulting from inverse trig functions. Okay. There. Okay. So now with this one, let's see what the actual important parts are. Well, there's just the three main formulas, which are important. And I was thinking, actually, there's one exceptionally hard question that Horowitz did that I want to do. So we'll try that one. But let's just write the main formulas here for now. So it's going to be the integral of 1 over square root of a squared minus u squared du equals sine inverse of there's no of on these. That's strange. U over absolute value of a plus c, like that. So that's our first formula. Second formula is 1 over a squared plus u squared du equals 1 over a tan inverse of u over a plus c. And finally, if it's 1 over u root u squared minus a squared, equals 1 over the absolute value of a secant inverse of u over absolute value a plus c. So these are the three trig formulas, and maybe if anyone has any suggestions, I'll do that first, and if not, I will do the question that Horowitz did.
Wait, so there's nothing in terms of like inverse cos, inverse cotangent?
No formulas that we use in this section, at least.
Alright, well, I hope they don't put it on the test.
Yeah, for sure. I mean, it's not part of not even in the textbook, so I would expect not, but who knows.
If you want, for session 2, there is like an exam review under Professor Sides.
His course
Kinda
material?
like, what is it?
Yeah.
Under
You can't
Sides
see
show.
it. If you're not in his class, you can't see it.
Oh, really?
Can you like download it and put it in the chat or something?
That would be
I
helpful.
can, yeah.
Yeah, I'll do that, I think. I don't know if I can do that. My laptop's glitchy, so someone else do that. Never mind.
Well, yeah, but if anyone can, that'd be good. Did I write the answer? Yeah, here. Okay, this one was just a weird question because you have to do a special trick in it. It's not actually that hard. You just kind of have to remember some quadratic stuff. So I don't know if the other teachers did this as well, but the example that Horowitz did was this example: the integral of dx over square root of 5 plus 4x plus x squared. Okay. So you can't do this by U-sub because there's nothing much going on. Just to make it a little more clear, I'm going to write the dx over here and just make that 1 over. Okay, so yeah, you can't do it by U-sub. It looks like it's going to be something to do with the with this one, with the sine inverse result, right? Because it's 1 over something squared minus something squared, but it's not in that particular set. It's not a difference of squares down here. So let's figure out what we need to do to actually make it a difference of squares. So what you got to do is you got to complete the square, right? So x squared plus 4x plus 5. So to complete the square, we want to figure out what will turn this into x minus a squared plus c, right? And hopefully that'll end up being a minus c, because then it's a difference of squares, right? Or at least hopefully c will end up being negative. So to do that, if you remember, we take the middle number, divide it by 2, and square it, right? So we get 4. That number we need to now put in here and add it in here, like that. Add 5 at the end, and then subtract 4. So we're adding and subtracting 4. It's okay. And we didn't get what I expected. What did I do? Negative. Oh, okay. Oh no, we'll get the right thing, I think. We'll still get the right thing. Let's see what happens. Oh, no. I wrote it wrong. I wrote the question wrong. There's a negative there. Okay?
Oh, okay.
There's a negative there. So there's a negative here. So I got to factor out the negative. So it's negative x squared minus 4x minus 5. Okay? Now, same process. Take this out, divide it by 2, and square it. I still get a 4. So I'm still going to add a 4 into here. So it's negative x squared minus 4x plus 4 minus 5 minus 4. And now I can just factor this right here, and that'll end up being 2 and 2. And so it'll be negative 2 and negative 2. So this is going to end up being negative x minus 2 squared minus 9. Right? And that'll finally end up being 9 minus x minus 2 squared. Or in other words, 3 squared minus x minus 2 squared. Great. I can put that in the denominator here. 1, so the integral of 1 over 3 squared minus x minus 2 squared. Now this is just the formula. This is just this now. A squared minus u squared equals u over absolute value of u, sine inverse of u over absolute value of a plus c. So this is equal to sine inverse of u, x minus 2, over absolute value of a plus c. And that's the answer. Let's make that nicer. And that's the answer for that one.
I'm just a bit confused. What did you do when you put the 4 there? Did you just add 4 to both sides?
Yeah, so definitely I understand people forgetting what completing the square is. But completing the square is pretty much you're turning any old quadratic. So I'll just again use this example, but it doesn't have to be this example. Here, I'll just take this. Negative x squared. Well, I'll just forget about the negative. Just say x squared plus 4x plus 5, right? Or plus 4x plus 5. Yeah, we're taking any old quadratic. This will factor into x minus 5, or sorry, x minus a, x minus b, right? We can factor it into 2 linear factors. We know that.
Yeah.
But completing the square, what that's doing is it's saying, well, what if this coefficient at the end was like the ideal, that's not really the word, but the ideal, not coefficient, but the ideal constant at the end to add. Specifically, the constant that would make this factor into x minus a squared, as in the 2 linear factors are the same, right? What would that be? Well, to find what that is, you take the middle term, you divide it by 2, and then you square that. So you get 4.
Oh, right, yeah.
So it'll be a 4 here.
It's just coincidental that it was 4.
Yeah, it's just a coincidence that it was 4 in both cases here, right? But yeah, so then it's a 4 there. And so then just to not change anything, you got to subtract a 4 at the end too. Because if you don't subtract a 4, then you've just added 4 out of nowhere, right? But if you subtract a 4, it's no big deal.
Yeah, thanks.
So then this middle thing, this thing here in the brackets will factor into something nice, and you'll just have a coefficient at the end. And in this case, that's helpful because we're looking for something in the form of a squared minus b squared.
The exact thing was on the final exam. like last year's final exam.
This question?
Yeah, exactly. Like not the same numbers, but like exactly same.
So there you go. And I only know how to do it because Horowitz is in the lecture. So that's why I know how to do it. But yeah, so then that's that.
Sorry, can you scroll up a bit?
Yeah.
Thank you.
Have some water. And so we'll start chapter 4, and then at 6:30 I'm gonna just take a little break. Okay, so 6:30 is we'll take maybe a 10-minute break or 15. Let's say 15-minute break, just so we get a little extra relaxing time, and then we'll keep going. So let's start. We'll still have 8 more minutes. So yeah, does anyone have any more questions for this?
Oh yeah, I wanted to ask, when are you like? How long is this gonna go for?
I always schedule it for 3 hours. So
okay.
If we finish sooner, we finish sooner. If we finish later, we finish later. I don't know, but I generally try to make it 3 hours.
Okay, that's good.
So you're gonna do 4 now, and then you're gonna do 6 afterwards.
Oh yeah, like chapter 4. Well, we're not gonna get through all of chapter 4, right? Right before the break. Right? Chapter 4 is a long one. So yeah, we probably won't even get to chapter 6 today. I don't know. Probably. I mean, we might, but I also haven't done any chapter 6 practice work. So maybe might not be that helpful.
Same.
For tomorrow, I'll hopefully have some done so that we can do some tomorrow at least. But yeah, as of right now, I have not done any chapter 6 practice. So.
All right, no problem. Thanks.
So, yeah, so we'll figure that out. Okay, sorry. So, chapter 4.1 is related rates. Again, unless anyone has any questions here, I'll move on to 4.1, which is related rates. And so these are special types of problems that use derivatives. So now we're not in the integral section anymore. We're in applications of derivatives. So there's no integrals here. In fact, none of these questions will even use the idea of an integral because this is chapter 4 before chapter 5, right? So let's see if I have any. I don't know if I want to use Horowitz's examples. Not really. Well, maybe I do because I have the whole solutions here. So pretty useful. Yeah, maybe let's do some of the ones that Horowitz did. Although the ones that Horowitz did were more complicated than the ones. Oh my god! Wow.
Could try CPWs. I think it's session 19.
I think CPWs is also private, so only his students.
Oh, it is.
So all the best professors you can't see, which is such BS.
Yeah.
Oh, sorry.
Okay, how about let's do this one? I like this. I like this question because it has a nice drawing. So let's do this question, and then probably after this question we'll take our break. So I'll just type it because it's a lot of writing. So water is being poured into a cone-shaped tank at a constant rate of 3 centimeters cubed per minute. And then the tank has a height of 3 meters and a radius of 1 meter. At what rate is the water level decreasing? Oh, it's being poured into it. Increasing when the water is 1.4 meters deep. Okay. Okay. So that's our question. But I'll put it all together in one thing like that. There we go. So I will draw the picture first. So we have a tank, right? We have a tank that's here. So I'll draw the tank. It's a cone-shaped tank. So we have a radius in the middle, and I would draw it bigger than that actually. How about this? Let's draw it like that. That's the bottom of the cone. Wow, OneNote is not very good at drawing lines. I'm gonna be honest. It's a kind of a pain. It's better just to draw it by hand. So, but I'll try my best. So there's that. Actually, you know what? I'll make the cone much bigger and less shorter. So there's the cone, and there's, yeah, that's better. Okay, there's a radius in the middle, going all the way up. I mean, height in the middle. There's our radius, and there is our water level. Okay, so our water level's there. It's like right there. This has a different radius, so I'll call that, well, I guess this is actually just 3, and this is r, right? We know that this height from here to here to here is 1.4, right, like that, 1.4 meters. Oh, and actually, no, I'm going to write everything in terms of centimeters because it's in centimeters per minute, the rate. So this is 140 centimeters, and this is radius 1. So it's 100 centimeters. And we know that this total height, this green height, right? And now I kind of covered the red line, so let me draw that back, right? The green height is 300 centimeters. Okay. So we're asking for at what rate is the water level increasing when the water is 1.4 meters deep. In other words, we're looking for dH by dt at when h equals 1.4. So looking for dH by dt when h equals 1.4. So what do we know? Well, we know that dV by dt, right, equals 3. Right, because it's being filled at 3 centimeters squared. It's supposed to be cubed per minute. So dV by dt. Now let's figure out what the volume of that cube here, what that cone is at the bottom here, right? So the volume of that cone, well, you need the formula for the volume of a cone. So the formula for that is V equals 1/3 pi r squared h, right? So
something just quickly to add, not really related to the problem, but it might help people. That if you think of an area of a circle, it's pi r squared, and then you think of an area of a cylinder, is pi r squared h. And then 3 cones fits into 1 cylinder, so that's gonna be 1/3.
Yeah, that's a good point. Yeah, I was actually tutoring someone recently, and like someone in a younger grade, and I was explaining that to them, and they were pretty impressed. That it's like some sort of graphic, like obviously it's geometric because there's a thing, but there's like a cool way to think about it. But yeah,
right.
Yeah. So that's the volume. We're looking for dH by dt. We're looking for dH by dt. So let's check here now. Yeah, so we don't want an r here. We don't want this r here, right? Because if I take the derivative of this right now, implicitly, right, I could, but I would end up with dr by dt here. I'd end up with that, right? So let's see what happens if I took the implicit derivative here. I'd see v prime equals 1/3 pi r prime h prime, right? So notice I interchangeably use dv by dt and v prime. So that might be a confusing thing that I do, but when I'm in the equation like this, I don't really want to write it as.
Wouldn't it be 2r prime?
Oh, you're right. There's a 2 here. Yeah. There's a 2 there.
CVW did this exact question too, just with like different numbers.
Yeah, because it's a good question. So we don't want this because look, r prime, we don't know anything about that. We know the radius, but we don't know r prime, and we don't really have any way of Maybe we have a way of figuring that out, but that's not how we're going to do it. What we're going to do is we're going to just relate r and h together, right? I'm going to get an expression for r, which is something happening to h. So I'll do that by taking a slice out of this, right? And I'm very, very bad at drawing the slices. But the slice kind of goes along the edge of this, right? The slice goes like that, and it kind of like cuts through this. I don't know, I can't draw it, but it cuts through that. And so what you'd see is you'd see a upside down triangle kind of like this, right? Here, that's our water level. So that's h, or no, sorry, that's 1.4. Well, which is h, sorry, which is h, right? This is r, right? That's r. And we know that this is 100, and we know that this is 300. Okay. So what I can do now is I can do a similar, I think we have two similar triangles here, right? Because this is theta. That's theta. Oh boy, someone went off in the microphone. Okay, that's okay, don't worry. So we want to relate, we can use our trig functions to relate these two sides, right? So if we're relating the opposite and the adjacent, right? So it's going to be tan theta is opposite over adjacent, right? So tan of theta, just looking at the smaller triangle, tan theta equals adjacent over hypotenuse, okay? Looking at the big triangle, right? The big triangle here, I'll draw it quickly, right? Tan theta, the adjacent is 300, and the hypotenuse is, oh, no. Oh, yeah, sorry, that's not hypotenuse. I'm just saying the wrong thing. Sorry, height. I'm just saying the wrong words, but the letters are right. Height and over r, right? So the adjacent over the opposite is the adjacent 300 over the opposite, which is 100 in this case, right? Which is just 3. Just make that a little simpler. It's just 3. Okay, well, we can make these two things equal to each other, right? H over r equals 3. So I will say r equals h over 3. Yeah, r equals h over 3. Never mind. What am I thinking about? Yeah, r equals h over 3. Good, I have an expression now. R equals h over 3. I have an expression for r, or for h. So I can go back to my formula here. V equals 1/3. So just to be clear, that was not correct to take the derivative there. To take the derivative there. So V equals 1/3 pi r squared h, right? I'll put that into here. So I'll end up with V equals 1/3 pi h over 3 squared h. And now I can take the derivative. Would I take the derivative now? Yeah, I will. So V equals 1 over 27, or I'll say pi over 27 h cubed. Yeah. And now I'll just take the derivative. I'll just do that normally. And actually, I'll leave this
Excuse me?
Mm-hmm.
Isn't tan theta supposed to be opposite over adjacent instead of adjacent over opposite? So it would be r over h?
Oh, yeah. How did I do that? Opposite over adjacent is h, r over h. Yeah.
It actually doesn't matter.
I sounded so confident. Yeah. Yeah. It doesn't matter, but you're probably right. But I'll just do it. Yeah. Sounded so confident saying that and didn't do it. So 1/3, right? Then I'm still solving for r. So I could flip both of these, and it would be r over h equals 3, right? Oh no, sorry. This is r over h, So h over r equals 3. So I still get this. So we're good.
Hey, at least you were consistent in your mistake.
Yeah. Well, yeah. At least I can fix it, right? So let's say v. So I can take the derivative now. V prime equals pi 3 squared h prime. Great. So now I can solve for, the question was asking for dh dt when h equals 1.4. So this is our dh dt. I can just solve for that, right? So it's going to be v squared times 9v prime, v prime, over pi h squared equals h prime. Now let's plug in all the numbers we know. 9 v prime is 3 over pi h is 1.4. And now I can just do this. So it's just it's just going to be 9 to the power of 3, well, whatever, I'll just say 9 times 3. Why am I making it more complicated? Pi times 1.4 squared. So my dh by dt, I guess I could leave it as the thing, but yeah, I assume that's the same thing as that he got here. So I got 4.38 centimeters centimeters per minute. Yeah. And I'm just going to check if that's the same answer he got. 20. He wrote it as irrational, so times 140. Oh, not the answer he got. Okay, let's see what happened. Oh, because this isn't 1.4. Sorry. This isn't 1.4. This is 140. Because they're in centimeters. That was in meters. So this will be not that answer. Well, it'll be 27 over pi times. Oh, times 140. I just didn't square it. I guess I just didn't finish writing the question for some reason. It has to be a square there. 27 over pi times 140. Yeah, I didn't write the square, but I think I just forgot to write it. There's no way that one. So this is what I had. I have as the final answer 27 over pi h squared equals dh dt, and then equals 27 over pi times 140. I must have just forgotten to put a square, and then we'd get the same answer. I mean, obviously, that's the answer. So not this. Just leave it like that.
Yeah, it's the same answer. I square it.
And there you go. Okay, so there we go. Let's take a 15-minute break, and then we'll keep going and do some, what's it called? Some related rates problems. And hopefully get a little further in chapter 4. Although there's not that much in chapter 4. I mean, there's quite a bit, but it's all seems simple and is confusing to me for some reason. So we'll see how it goes. But yeah, so let's take a 15-minute break. Let me put that OBS thing on. AFK. Back at not that time. Back at so let's say it's 55. So 6:55. Okay, guys. So I will be back then. Everybody take a breather. Okay, guys, I'm back. Everybody else here still? Hope so.
Hi.
Yes,
Yeah.
hi. There we go. I'll start back up. We got that happening. I think if I minimize, it's still working. Okay. So, okay, let's keep going with some water. Let's keep going with some 4.1 practice. So, I guess I'll do some more of the questions from Horowitz's lectures, unless anyone has any suggestions from the book or anything like that, and I'll do that. But otherwise, I think I'll do this one. Well, there was one that I did with James. I don't know if James is here, but we did with James, and it was like the question in the textbook that was, if I find it, with the ladder, or not ladder, with the oh no, that wasn't related rates. That was an optimization question. Never mind. I was gonna say that was never mind. That was an optimization.
Was that the one with the door hinges, or
with the I'll find it. This question, 323.
Oh yeah.
With the L.
I
with the
did that today. God.
Yeah.
It's not as hard as it like seemed at first, but I was
Yeah,
like, how do I?
So does anyone have any suggestions from these sets of questions, these sets of problems? If not, maybe I'll do one more, and then I'll just carry on. So maybe if people can suggest one more. Yeah. Otherwise, I will just do one from Horowitz's lecture. So I guess I'll do that. So cone-shaped thing, that was good. Okay, I'll do this one. Seems to be all right. Just don't have the final answer. So the base of a triangle, or wait, hold on. I think I saw a hard, like a one that looked harder. Hold on. No, this should work. So the base of a triangle shrinks at a constant rate of 1 centimeter per minute as its height grows at a rate of 5 centimeters per minute. How much is the area changing when the triangle has a height of 22 centimeters and a base of 10 centimeters? Okay. That's good. So we have a triangle that looks like this. Okay. And it has a height h and a base, and its area is 1/2 base times height. So I want to, what do we know? We know that dh by dt equals base is shrinking, height grows 5 centimeters. db by dt equals -1. We know that the time we're looking for, the height is 22 and the base is 10. And what we're looking for is dA by dt. Oh, we just take the derivative. Yeah, don't we? Okay, this was easier than I thought. We just take the derivative. Is that what it is, really? HDH. Yeah, we just take the derivative. That's all it is. Okay, well, it was easier than I thought. 1/2. A prime is 1/2 b prime h plus bh prime, right? A prime is equal to 1/2. Now let's put in the numbers we know. B prime is -1. The height is 22 plus B is 10 plus H prime is 5. And we just do that, right? So this is 10, so I'll just say this is a 5 and this is 11, so that cancels. And then, so this is A prime equals -11 plus 25, which is third 14. That looks right. Okay, there you go. That was a lot easier than I thought. Never mind. So I thought that was going to be a harder one. Yeah. Okay, any other suggested problems?
Can you do 41? Yes. Or maybe just go through it. You don't have to do it if it's too long.
Let's see. Well, we can probably do it. 41, is that part of the suggested problems?
I think it is. It's like the last.
The last one, yeah. Then I did do it, so let's see. I'll take the screenshot. And hopefully the screenshot works because I've been having trouble with the screenshots. Yep, it worked. So you are walking to a bus stop at a right angle corner. Oh yeah, this was a good one actually. You are walking to a bus stop at a right angle corner, and at that many. Oh no, I moved something. You move north at a rate of 2 meters per second. So you're moving north. And you're 20 meters south of the intersection. The bus travels west at a rate of 10 meters per second. Right, so 10, 2. You missed the bus. What is the rate at which the angle between you and the bus is changing? That's theta. It's changing when you are 20 meters south and the bus is 10 meters west. Okay, so just to be clear here, actually, this is call this y, call this x, right? We know dx by dt. We know that that's 10 meters per second, so 10. We also know dy by dt is 2. We know x is 10, and we know y is 20 at the time we're looking at. And so we're trying to find d theta by dt, right, at those times, when these things are true. So let's find a relationship between all these three things. What I guess I'll do is I'll just say tan theta equals opposite over adjacent, so x over y. So there's our thing. Now I can take the okay. Yeah, okay. So then I can just say, well, the derivative of tan is secant squared. Can someone confirm that? I don't have it in front of me. It's secant squared, I think. So is that right?
Yeah, you're right.
Yeah. Okay, thank you.
Yeah.
And then I'll just because I don't like the rule. This is x, y, -1. So the derivative of the first one times the second one plus the first one times the derivative of the second one. So now we can just rearrange this for theta prime, right? So this is, I guess I'll combine these first. So by combining those, I'm pretty much just doing quotient rule, but it's fine. So y minus x over y squared. Yep. Y minus x over y squared. Good. And then what I can do after that is just divide both sides by secant squared. So theta prime equals y minus x over y squared secant squared theta. Oh, we don't know theta. Oh, we can find theta. So theta equals, in this particular case, in this particular case right here, theta equals tan inverse of x over y, right? Which is tan inverse of tan inverse of a half. Someone's got their mic on, and people are talking in the background. Maybe they can, I don't know who it is. 1/2. Okay, well, oh, am I in the wrong mode? No. I guess I'll just leave it as, tan inverse. Theta equals tan inverse of a half. Sure. So if I plug that all those numbers in, I'll say theta prime equals 20 minus 10 over 20 squared secant squared, and theta is tan inverse of 1/2. Okay, and just to be clear, let's put the squared out there. Okay, so theta prime equals 10 over 400 times that thing, which I'll just leave blank for now. So that thing in there, we're saying secant of tan inverse of a half. So we're saying theta, or actually I won't call it theta, but I'll call it phi, I guess. Phi equals tan inverse of a half, right? Or no, maybe I should call it theta actually. I don't know. We'll see. Whoops. I don't know. We'll figure it out. So so tan phi equals a half. So but we're looking for secant of that theta. Oh, so it is theta. We're just gonna call it theta. So we just call it theta. But we're looking for secant theta. Secant is 1 over cos. So if cos is adjacent over hypotenuse, secant is hypotenuse over adjacent. So let me write that here. Secant is hypotenuse over adjacent. So tan is, of course, opposite over adjacent, right? So that means we have a triangle like this. The opposite is 1. The adjacent is 2. So the square must be 1 squared plus, the square root of 1 squared plus 2 squared. So square root of 5. So root 5. There you go. So the secant of that same angle, if this is our theta, secant of that same angle is going to be hypotenuse over adjacent, so root 5 over 2. Okay, secant equals, so I should say secant theta equals root 5 over 2. So this is going to be root 5 over 2. So theta prime equals 10 over 400 times 5 over 4. So 500, 10 over 500, 1 over 50. And that's my answer for that one. Which I don't know if that's the answer. Is that the answer for the question? Maybe someone got the answer. Let's see. I'll pull it up. This was 41. Chapter 4? Yeah, chapter 4, number 41. Oh. Wait, no, sorry, this isn't 41. What was I doing? Oh, yeah, sorry. Wait, hold on. Okay, no, I'm doing the same question. Not the answer. Let's see. I feel like I lost track of what the question was. Theta is that. Okay, not the answer. Let's see what the answer was. Unless I did some just mental math at the end, you're wrong. 11 over 25. Not 1 over 50. Did I do this wrong? Let's just see what 10 over 400. Yeah, no, that should be right. 400 times. I'm not saying my numbers, like, the answer's obviously wrong, but my math at the end here is right. So where'd it go wrong? Let's see from the beginning. You are walking at a bus stop to the right angle. There's the right angle. You're moving north at a rate of 2 meters per second. dy by dt is 2. That's y. The bus travels west at a rate of 10 meters per second. dx by dt. Oh, this is negative 2. Y is getting smaller. The value of y is getting smaller. Yep. So here... Oh, and I'm missing a y prime. And I'm missing a y prime there. Yeah. And I'm missing a y prime. Here. Here. So this is a negative 2. And so then this is going to be a negative 2 here. Negative 2 here.
Why would it be negative 2?
Well, because the y, the value of the variable y is getting smaller because you're running up towards the corner.
Okay.
Right?
Yeah.
X is positive because that value is getting bigger. That length is getting bigger.
Yeah. When you differentiate, did you have any like x primes? I don't think you did, right?
Yeah, here. When I did this stuff, I did there was a y squared on the bottom. And then also secant squared, but that was after that's like during the process of it. I do kind of product rule and quotient rule like weird. So, yeah. Like I treat it like a
Shouldn't there be an x prime though?
What'd you say? Sorry?
Shouldn't there be like an x prime?
X prime
dx over dt.
Derivative first one. Oh, you're right. Yeah. So I just messed up the implicit. Yeah, you're right. So I treated them both like x's for some reason. Yeah. So there should be an x prime here. This is the derivative of the first one times the second one, x prime, times that. So then here, this would be there's an x prime here. And then this is literally just quotient rule, right? This is literally what it looks like, right? So then there should be a 10 here too. Yeah. So I made a bunch of mistakes. So this is negative, just call this negative 20. Let's see if that does it. This is a negative 20, negative 20. Let's see if that fixes it. So negative 20 over 50. No, that's not right. I'm just doing too much math in my head. 10 times negative 20 over 400 times 5 over 4. Yeah, I still got negative 5 over 2, which is not the right answer. Or negative 2 over 5, I mean. 2 over 5. So let's just keep going from the beginning. What did I get wrong here? So y is negative, y is 20. You are 20 meters south, so y is 20. 10 meters west, x is 10. Okay, looking for d theta dt. So tan theta equals x over y. Tan is opposite over adjacent, opposite over adjacent, x over y. Yeah. The derivative of this, okay, is going to be secant squared theta prime. Then it's the, let's take this here, let's take this dt of that.
Would it have mattered if you like moved the tan inverse before you derivated, or it'd still be the same thing?
It definitely wouldn't look the same, but I think it would get us the same answer.
Okay.
Yeah. So the derivative of this is going to be, okay, so the derivative of the first one times the second one plus the first one times the derivative of the second one. So the derivative of y to the negative 1 is negative 1 times y to the negative 2 times y prime. So that's negative xy prime over y squared, which is what I wrote here. Okay, that's right. So then multiply this by y, top and bottom, yeah. So it's x prime y squared, okay. Divide by secant squared theta. Yeah, looks like it should be okay. So then this is going to be, on the top here, this is going to be x prime was 10 times y was 20 minus x, which was 10, times y prime, which was negative 2. Okay, over y squared, 20 squared, times secant squared. I did square it. Never mind. I did square it. Did I do this right? Secant. If I just, well, no, I can't just type that in, can I? Well, 1 over, can I just type in 1? 1 over cos of tan inverse of a half. Answer over root 5 over 2. Yeah, okay, so that is, I did this whole thing, right? That is root 5 over 2. So the top will turn into, that's 200 plus 20. Is that right? Yep, looks right. So 100 plus 10. And that's a 200 there. So I just put 110. So this should be, yeah, 110 over 200 times that. Let's see. 110, 200 times 5 over 4 is 11 over 25.
Yeah.
Okay, we got the answer eventually. 11 over 25 times radians per second. And yeah, there you go. So there's that problem. How does everybody feel about that? Especially the person who asked me to do it. So hopefully that made sense. I'll move on to 4.2 if nobody else has any more questions for 4.1. Although 4.1 has a lot to it, so we missed some stuff. I mean, that's just like more questions like this.
By the way, guys, test 2 grades are out.
Oh,
so
I will check that right after this.
Really? I don't even want to check it.
Yeah.
Yeah, you probably shouldn't now because probably everyone's just like swarming Bitcoin right now.
Anyway.
Yeah, so I'd rather check later. But Horowitz made like an announcement. They might consider curving it, but
even for calc
until after. Yeah, for calc, but that's after like test 3. But that's after test 3. If we do well on test 3, then he might curve it. If we do well, then probably not.
Wait, they updated on D12 too.
Yeah.
I don't want to check it. I'm going to be depressed for the rest of the 2 weeks, so I'm just not going to check it.
Just going to leave it?
I already checked it and I'm kind of depressed.
Yeah.
Exactly why I don't check my marks.
Yeah.
Maybe I'll have to check it tonight because if I have to drop it, then.
Yeah, you should definitely know that. It's today the last day. Tomorrow's the last day.
Yep. Well, yeah, tomorrow's the last day, but
yeah. Well, good luck, everybody. Hope everybody did well. I don't know. I have no idea how I did, honestly, but we'll see. We'll see how it goes. So 4.2 is linear approximations and differentials. Honestly, I didn't get it that much. This like I could do the linear approximations. It's fine. Differentials was fine. I couldn't even do. I didn't actually really give it a good shot of doing the error thing, so I don't know if I can do that. But the main thing to understand from this is this, right? The linear approximation of f at a is f of a, well, better to move it around, f prime of a times x minus a plus f of a, which is just like the tangent to the slope. That's how you would do the tangent to the slope. And so we can do, what we can do with that is we can just approximate things that are close to useful things, right? So that it's useful. So let's try one. Here, how about this? Find the linear approximation of f of x. Oh, so let me write this here. So this is, oh no, I'll write it in thing 4.2. Linear approximations and differentials. So f of x equals sine x is our function. We're approximating it at x equals pi over 3. So we just do the formula, right? So we say the linear approximation of x, right? So f of x is approximately equal to L of x, which is equal to, so f prime of pi over 3, x minus pi over 3, plus f of pi over 3. So f prime of pi over 3 is going to be, so f prime of x equals cos x. So f prime of pi over 3 is cos of pi by 3, which is a half. So this is going to be 1/2 x minus pi over 6 plus sine of pi by 3, which is root 3 over 2. Okay. And then we have...
What the hell is it?
Oh, so someone saying something, or I guess not. I guess they just, yeah. And then we just add these things together. So I guess I'll just say this is a 6 at the bottom. So then I'll just say this is 1/2 x minus pi plus root 3 over 6. Is that right? Oh, I guess they didn't multiply it. Oh, probably best to not multiply it, actually, but whatever, we're here. We're going to estimate what sine of 62 degrees is. Okay, so we want to know sine of 62 degrees. Yeah, so we're actually just saying, since the function was sine of x, I'm pretty sure we just put in 62 degrees, but in radians. 62 degrees. Did we do that? Yeah, 62 degrees. The conversion is pi over 180 degrees. So 62 pi divided by 180 is not something nice. Not anything nicer than what you'd expect. 31 pi by 90, which makes me think something's wrong here. Oh no, they just used that. So we just plug that into the formula, right? So we just say, well, that's 1/2, so it'll be 31 pi over 180 minus pi plus root 3 over 6. And let's see if that's the answer. So 31 pi over 180 minus pi plus root 3 over 6 is not the same answer as what they got. So let's see what I did wrong. Let's see here. So I'm trying to find L of that. So just that x value. 31 over 180 is pi over 6. Oh, this is 3 root 3. This is 3 root 3. That's 3 root 3. Still get a negative of what they have, or not even. Still not quite. That's strange. Why do I get that? That is strange that I get... I pretty much have the same thing. I really pretty much have the same thing. I don't quite know. Negative root 3. I guess this is not correct here. That's not right. So I'll flip this around. This is 3 root 3 over 6 minus pi. Let's see if that does anything, because I think the negative is kind of screwing us up here. Yeah, this negative is screwing us up there. So 3 root 3 minus pi over 6. So this is 31 pi over 180 plus, it's plus there, plus 3 root 3 minus pi over 6. And now I get what they said, which is approximately equal to 0.8835. Okay, there we go. So f of x is approximately L of x, which is equal to this. I turn that into this. So f of pi over 3 is approximately equal to L of pi over 3, right? Which equals that. Sorry, it's messy. That over there. And then so approximately equal to 0.8835. Mistake was just I should have just left it as simplified as possible. I didn't have there was no need for me to do that, funky fraction thing. So I just converted 62 degrees into radians and put that in, right? Sorry. So we were looking for f of 31 pi over 90. That's what we were looking for. Sorry. 31 pi over 90, right? And so we plug that in here, and we got it like that. Yeah, okay. See, these things are like, to me, they're just like confusing, and I get them wrong sometimes. I don't know why. I don't even know what to say about differentials. I don't really they're just like, you just make it a variable. Make dy dx a variable. Make it a fraction. Let's see, what else is there? Let's see, I'm going to put this here actually. Estimating about a function change as a result of a small change in input values. Just make them actual variables. Right, so you can multiply both sides by dx here to get, instead of dy dx, you get dy equals f prime of x dx. Yeah, I don't know what to say. For each of the following functions, find dy when x equals that. So you just take the derivative. It'll be dy by dx. Well, let's do b, I guess. So let's do a. Why not? So it's saying for this function, y equals x squared plus 2x. Okay. Find dy when x equals 3 and dx equals 0.1. So dy equals 2x plus 2 dx. So dy equals 6 plus 2 times 0.1. dy equals 0.8. I don't really know what else to say. It's just like you just plug it in. You just plug in the numbers and you treat them as variables. The only thing I don't know how to do, and maybe let's figure it out together, is to do the error checking.
Yeah, I was gonna ask about those because CPW technically didn't do those. I don't know if they're gonna cover those on the test.
Let's see. Well, Horowitz did do it.
He did. Oh.
He did do it.
Does anybody know if any other professors did this in class? Error.
I think maybe Dr. Side covered it, but it was really brief. So we didn't really do much on it.
It was very brief. Is there any on the practice test?
I haven't checked. I'm not sure.
If anybody has, but
Wait, we're talking about linear approximation?
Linear approximations maybe, but differentials and error approximation.
Yeah, I don't think there was one on the practice exam.
Yeah,
okay, that's fine.
So well, we can do one of these problems that Horowitz did. Delta y is.
Isn't just differentials just differentiating?
Yeah, it's just treating dx and dy as variables. Right?
Like you find dy over dx and then you just put dx on the other side. That's it.
Yeah, and you can just do it multiply both sides by dx and all that stuff and
whatever like that.
It's useful for, I guess, for error approximation, although I don't. So maybe how about this? I'll I'll try to figure it out before, because I really don't know. So I'll try to figure it out before next session, and maybe we'll talk about it then, because I really don't know anything about the error approximation.
Oh yeah, so if you have like a function like area, for example, in terms of radius or something, so dA will be the error in that area. That's all it is.
dA.
Yeah, so if you have ax as a function, a in terms of x as a function, then dA over dx will be the error, the error in the area.
Oh, okay. I guess so. That makes sense. It wouldn't. I have to do a problem, like a practice problem with that, right? But I think the next couple sections are also pretty nothing. I'm gonna be honest. Pretty. I don't really know what to tell you about them. We'll definitely talk about them. The next one's Maxima and Minima. When the derivative is 0, you have some sort of critical point, right? So, like that's an absolute maximum and a local maximum. Here actually it says no absolute minimum. Yeah, sorry. Then so it's kind of self-explanatory, I think. But unless if someone has questions about it, of course, don't you can ask me. But only thing is to understand, I think, is that the critical points exist when the derivative is equal to 0. So just take the derivative, set it equal to 0. That's where your maximum or minimum are going to be. Unless you have a bound, in which case you have to check the bounds as well. But then just compare all those, right? Yeah, let's skip that. What about these things? Note that these graphs do not show all possibilities. Yeah, we see several possibilities for critical points. In some of these cases, the function have local extrema and at critical points, whereas in others the functions do not. Note that these. Okay, so how do we deal with that then? Oh, so you also have to check where the function is undefined. Yeah, okay. Where the derivative is undefined. Sorry, where the derivative is undefined. So that's everywhere you check for local and absolute maximum is where the derivative is equal to 0, where the derivative is undefined, and where at the edges of your bounds. Right. So, locating critical points. Well, how would I do it? Well, I take the let's do it for this C here because that looks like the most complicated one. Although I don't think any of this is too bad. So C is asking f of x equals 4x over 1 plus x squared, and is asking for where's the critical points to all these. For each point, find all critical points. For each of the functions, find all critical points. So, sorry. So the I'll write this alternatively as 4x times 1 plus x squared to the negative 1. So to figure out the critical points, well, I got to find the derivative, right? So the derivative of the first one is 4 over 1 plus x squared plus the first one times the derivative of the second one. 1 plus x squared to the squared times 2x. Because the derivative of the inside here. So we will figure this out. So 4 over 1 plus x squared, and actually I'll say this is 4 times 1 plus x squared. Erase that. Over, so this is going to be minus 8x squared over 1 plus x squared. And so I just need to see, well, where does this not exist, first of all? Okay, well, where does it equal 0? Where does it not exist? So where does it not exist is what I'll do first. So it doesn't exist when the denominator is equal to 0. So when 1 plus x squared equals 0, right? So when x squared equals, x squared equals negative 1. So never, no real roots of that, right? So x equals plus or minus root negative 1. So not that. And then, so it doesn't exist there, and so there's no points where it doesn't exist, so we don't have to check any of those. Now we just check where it's 0. So where does 4 plus 4x, let me write it a little nicer. 4 plus 4x squared minus 8x squared equals 0. So that's 4 minus 4x squared. Where does that equal 0? Where does 1 equal x squared? X equals plus minus 1. And there's no bounds, so we just have to check plus and minus 1. So we're going to evaluate the function itself, at plus and minus 1. So f of 1, well, I guess I'll start with negative 1, equals, and f of 1 equals that. So f of negative 1 is negative 4 over 1 over negative 4 over 2, so negative 2. And f of 1 is 4 over 2, so 2. So that means I have an absolute. Doesn't mean I have an absolute. I definitely have a local minimum. Definitely have a local minimum here. Definitely have a maximum, local maximum here. Do I have an absolute one though? I don't see why not. Yeah. Yeah, I think so. I think that's right. So let's graph it just to see what it looks like, but it should be right. So here. Oh, did I not do it? Okay, it does. That is most of the screen. So it was 4x 1 over x squared. So 4x over 1 plus x squared. Yeah. So plus and minus 1 is where I said the local extrema are, right? So I can't click it. At 1, we have the local maximum, and it's also the absolute maximum. And at negative 1, we have the local minimum, which is also the absolute minimum. And yeah, there you go. Okay, so that's that. I think that's all I'll do for chapter 4.3. I don't know if there is anything else about it. There are harder ones because remember, so just to keep in mind, everything you should check for critical points are 1, where f prime of x equals 0. Okay, 2, where f prime of x does not exist. Oops, does not exist. And 3, the boundaries of your region. Boundaries of interval. In this case, there was no interval defined, so we don't have any boundaries to check. The derivative existed everywhere in the real numbers, so we didn't have to check that one. So we only had to check where f prime of x was equal 0, which was plus and minus 1, which is there. So yeah. Then that's everything. So does anybody have any questions for 4.3? Couple seconds, but I think we're good. So otherwise, okay, we skipped 4.4. So derivatives and the shape of a graph, that's our next bit. So derivatives and the shape of the graph, well, I think I can sum this up pretty quickly. So if we have this as our function f of x, right, then we have a couple critical points, right? These are our critical points. There's another one right there. These are the places where the derivative equals 0. And nothing really happening here. We also have something called, so let's start with that. So this is where the derivative equals 0. F prime of x, so I should write it differently. F prime of x equals 0. I'll just write it again. F prime of x equals 0. F prime of x equals 0. F prime of x equals 0. And nothing going on over here. In between these ranges, well, it can only either be positive or negative. It won't switch from positive or negative because it would have to pass through 0 to do that, right? So we sort of like separated our function into a couple ranges, right? From here to here, here to here, here to here, and there on. So let's just check any point in here. Well, here it's the tangent would be like that, so the f prime of x is positive. Here the tangent would be like that, so f prime of x is negative. Here the tangent would be like that, so positive. Here it's negative, right? Here the tangent would be like that, so it's positive, and it'll be positive forever, assuming it doesn't do anything else, right? And so sure, like that was good, yeah. That's the first derivative test, pretty much what we just did there, right? Without an actual function, but just drawing something. Then we have our second derivative test, and that's more about concavity, right? That's more about what kind of U shapes can you fit in here. So this is kind of concave down, right? The rate of change of the slope of the tangent is negative. It's getting more and more negative in this section. In this section, it's getting more and more positive, right? This section is more and more negative, and this section is more and more positive. And then here, again, more and more. Well, not necessarily more and more negative, honestly. I don't know, we can't really tell what happens after that. So once again, we have these points called inflection points that are here, right? So, my graph is not very nice, but we can kind of say like, here it's going like that, and kind of like here is an inflection point. Where it goes from concave down to concave up. And then I'd say like, here is another inflection point where it goes from concave up to concave down. And then like right about here is another point where it goes from concave down to concave up. Right? And then we don't know what happens after that. Let's assume there's no more inflection points after that, okay? These points are similar to where f prime of x equals 0 are critical points. Inflection points are where f double prime of x equals 0. Right? So f double prime of x equals 0. F double prime of x equals 0. So you can solve for them like that, right? So just get f double prime of x and just find where it equals 0. Then we can again separate our interval over a bunch of ranges, right? So we can say from here to here, from here to here, from here to here, and here to here. And you can't go from concave up to concave down anywhere except a inflection point, right? Okay, unless maybe should we check again where it's undefined? Well, there's nowhere is undefined here. I'm thinking in another example, but for now, let's just say this is where f double prime of x equals 0, so there's no other way for it to switch from concave up to concave down. So here it's concave down, so it's negative. The second derivative is negative. Second derivative is negative. Second derivative is positive. Concave down, second derivative is negative. Concave up, second derivative is positive. And this is kind of, well, slope. Yeah, hold on. There is an inflection point. There's an inflection point right here. And there's kind of another inflection point right there. Just because of how I drew it. This is definitely a concave down kind of thing happening. But then this is kind of a concave up kind of thing happening. You see what I mean? I guess I should draw it on that side. So let's just extend the graph a little bit here. It looks like that. So in this interval, it's concave down. And then afterwards, it's concave up. Just because of how I drew it, I don't want to be more precise. And kind of technically it looks like there's an inflection point here too, so that would be concave up. Yeah. So all those you'd find all those points on an actual function by just seeing where the second derivative equals 0. And let me make sure, is it just where the second derivative equals 0 or also where the second derivative is undefined? Suppose f prime of c equals 0. F double prime of c is continuous over an interval containing c. Okay. If the second derivative at c is positive... Oh, no. This is something... I'll talk about that in a second. Okay. So the only other thing that seems to be in this chapter is that how do you, just without looking at the graph, how do you prove that this is in fact a local maximum? This is in fact a local minimum. Well, what you do is you check, right? So the first derivative is 0 here. The second derivative is going to be negative if it's a local maximum and positive So f double prime of x will be positive if that's a local minimum, and f double prime of x will be negative if that's a local maximum, right? So that's a good way to just like check without graphing. I don't know any other way really, but yeah. Okay, anything about 4.5? Anything about 4.5 that you want to talk about? See? Let me know. Someone sent me something. Let me just see. Oh, someone sent me a double substitution question. Let's actually try that after, yeah. Maybe let's try that now, actually. Someone 2 hours ago sent me a double substitution question, and I did not see it. So maybe let's do that. But yeah, any other questions about 4.5? Otherwise, I'll move on to 4.6. And then I think after 4.6, I'll stop at 4.6, do that one question that people suggested, right? And then that one person suggested. How do you do questions? Okay, so someone asked what do questions look like from 4.5, from derivatives, this stuff, and how hard can they be? Yeah, not very hard. I don't think so. So you would have a question like this, where you get a function. You want to find where the local extrema are, right? Where the local extrema are, and just so where the second derivative is, where the first derivative is equal to 0. Decide if those are maximum or minimums. All these skills, I think, are actually used for being able to graph a function, which is a part of this. Yes, it is part of this chapter, actually. I think at the end. Right, no problem. Let's see, did they talk about graphing? At this point, we have enough tools to provide accurate graphs of a large variety of functions. Yeah, so all this is kind of to figure out like where, what we need to know for graphing these functions. I could do a graphing example. I haven't done a single practice problem for graphing because Horowitz said, not that it wouldn't be on the exam, but they wouldn't just give us straight up just like graph this function. So there might be something related to graphing on the test 3, but there won't just be a graph this problem. And even if there was, I think I'd be able to figure it out. Just figure it out. But if people maybe request it for tomorrow, I'll do one tomorrow, right? So let's move on, I guess, to applied limits at infinity and asymptotes. And from here, I will probably finish there for today, for just at limits at infinity, this chapter. And then tomorrow we'll continue with these applied optimization problems, L'Hopital's rule, and then we'll get into what chapter 6 is, the integration, applications of integration. Okay. So limits at infinity are what it sounds like. It's taking a limit as you go to infinity. So if you think about it like this here, I guess it's probably better to just get a picture, but if you say the limit of f of x as x approaches infinity equals some number L, right? It equals something. That means that the function does something over here, but as you keep getting bigger, it approaches the line, which is, if I can draw it nicely, the line which is y equals L. Right? It doesn't really matter what it does, but as x gets bigger, right? As x gets bigger, positive x, it'll approach that line. Right? Similar for negative infinity, right? So you'd just be going in the opposite direction, but still approaching some line y equals L. But let's figure out how to actually compute it. And so that means you have a horizontal asymptote there. Let's just do some of the homework practice questions, because I did a couple of those and they were fine. They worked out. So these are all just sort of identify where things are. I'll just skip that. Let's do, the homework starts at, what are we on, 4.6? 4.6. So 251. I guess I didn't finish it. Did I not finish it? 4.7. No, I think I just didn't scratch it off. That's the only problem. Yeah, I know I did finish it. 2.51. Yeah. Okay, so 251 is here, so we don't do that. We go to 283, so 57. So the question is, actually, I think I'll just skip to this. Evaluate the limit. Yeah, let's just start with evaluating the limit. So we'll do a couple of these. So 261 is evaluate this limit. The limit as x goes to infinity of 1 over 3x plus 6. 1 over 3x plus 6. And so a lot of these questions kind of end up just being like, oh, I guess it doesn't exist. Or like, oh, I don't know. That's, for me, at least, that's what it's like. A lot of chapter 4 is kind of awkward ending to questions. So as x goes to infinity of this, well, the denominator is going to get bigger and bigger and bigger, right? So this is going to approach 0, right? It's going to 1 over, yeah, it's going to approach 0. So I'm pretty sure this is equal to 0. Now, I say I'm pretty sure. Let me check. What question is this? That's with L'Hopital's rule. Let's see this one. What question did we just do? 261? Yeah, 0. There's the answer there. So 263, let's take a look at that. So this one is going to be the limit as x goes to infinity of x squared minus 2x plus 5 over x plus 2. So to solve this, well, what we do is we say, what's the most important term here, pretty much? What's the most important term that's happening? Well, we can't really cancel anything off the bottom, but as this goes to infinity, the x squared is going to get a lot bigger than the 2x, and especially bigger. The 5 never gets bigger, right? So these don't particularly matter. And so what we say is that we really have 2x over x plus 2, or just 2x over x, right? This is I hope this works. Yeah, okay, this should work. 2x over x, that's really all we have, because again, the 2 doesn't really matter. And we can cancel one of the x's, so we really just have x. And what's the limit? What's the limit as x approaches infinity of x? Well, that's just infinity. So the original limit was also that. It is identical, that process that I just did is identical to this idea of saying the limit, and this is kind of more practical, I think, is to divide the top and bottom by the highest power of x that is in both of them, right? So this would be x. So I would say 1 over x times x squared minus 2x plus 5 over 1 over x times x plus 2. So this would be the limit as x goes to infinity of x minus 2 plus 5 over x over 1 plus 2 over x. And so applying the limit now, well, we have this will go to 0. This will go to 0. This is just over 1, so the denominator doesn't matter anymore. And then we just have infinity minus 2, which is just infinity. Right, so 2 ways to get the same answer. Okay, so 265 is maybe another good example of this. Or maybe let's do 260. Yeah, 267 was actually good, because this is I had trouble with and James helped me. So 267 is the limit as x goes to negative infinity of the square root of 4x squared minus 1 over x plus 2. X plus 2. So for this one, we also divide the top and bottom by the highest power of x that we have in both of them. So since it's kind of like a x root x, the highest power we actually have is x, right? So we can divide both of them by 1 over x. I mean, multiply both of them by 1 over x. By both of them, I mean the top and the bottom. So to put that into the square root, I'm going to have to square it, right? So it's going to be 4, it's going to be the square root of 1 over x squared times 4x squared minus 1 over 1 plus 2 over x. limit in here again. Limit as x goes to negative infinity. Okay. So I will. Did I make a mistake? Let's see. Yes. Well, let's see. Limit as x goes to negative infinity. Now this will become 4 minus 1 over x squared. So the square root of 4 minus 1 over x squared over 1 plus 2 over x. Yeah, I did do something wrong. Let's see. Is someone telling me in the chat that I did something wrong? No. So the reason I did something wrong is because, look, okay, well, let's apply the limit. Oh, no, maybe this will work. No, this will not work. Okay, never mind. So if I apply the limit, okay, this is going to get more and more and more negative, right? More and more and more negative. So it's going to be 1 over negative 0. So it doesn't particularly matter. It's just going to be root 4 over 1 minus 0, which is just 1, which is just 2. The problem is that the answer is negative 2. That's actually the answer. And I remember that just because I just remember that. How did I not get that answer? Doing this. Where did I make the mistake?
Isn't it like positive and negative too? Because of the root. So.
It's, yeah, you're right. You're right. Okay, that kind of makes sense. So this would be 4, this would be root 4, and we'd only take the negative root because we're going to negative infinity.
I guess.
In Saeed's class, he over the root he factored out the x squared and then he squared it out, so it becomes absolute x. Mm-hmm. So when it becomes negative infinity, it becomes negative x.
Yeah, that's how James did it. Is James here? I don't know, but when he sent me it, no, he's not. But he did it like that, and that makes sense. I'll do that right after this, but I just want to know why this didn't work. I don't know why. I'm trying to figure out why it didn't work. Where did I lose the negative? X is okay. Well, let me do what they're suggesting and what James did, right? So 267. Write it again. So limit as x goes to negative infinity of the square root of 4x squared minus 1. What is it? 4x squared minus 1 over x plus 2. So the other way to do this is to factor out an x squared from here, right? So this is equal to the limit. I'll just say limit, but you guys know what I mean. So it's going to be 1 over x squared times 4 minus 1 over x squared over 1 over x times 1 plus 2 over x. Kind of a backwards way of doing it, right? Oh, hold on, but I still don't know
what are you going to do 1 over x squared?
It'll be negative x squared.
It'll be just x squared and x.
Oh, yeah, you're right. This would just be an x squared here. This would just be an x squared.
Oh, yeah.
And this would just be an x. Yeah. I don't know why I was just factoring wrong there. Okay. So, yes. Okay, good. So we're good. So now what I can do is I can pull that x out, right? So that x is going to be the limit so pulling that x out is going to be the square root of x squared times root 4 minus 1 over x squared over x times 1 plus 2 over x, right? So now the square root of x squared is the absolute value of x, right? So this is the limit of the absolute value of x times the square root of 4 minus 1 over x squared over x times 1 plus 2 over x. And since we're going to negative infinity, right? They're going to negative infinity, well, we can actually just replace this with negative x. Okay? Cancels the x's. And then just apply the limit. Right? So then just applying the limit, I have negative root 4 over 1, which is negative 2. So we get the answer. And that makes sense. I mean, this makes sense every step here. I just don't know why this didn't work. That's the thing that doesn't make sense to me. So maybe if someone has an idea why it didn't work.
I guess it's because it's not a polynomial and it's a square root. It's only supposed to work if you have polynomials like that.
What's only supposed to work?
Like the dividing by the highest power thing.
Well, you kind of did it here anyways. Yeah.
It was just after you had factored around. I don't know.
I guess so. I guess, yeah. It seems like I'm doing pretty much the same thing. I know what you mean. This is not just a standard polynomial, so maybe that doesn't work like that. But I don't really see why it shouldn't work. Everything should, like, to me, everything should work here. But maybe someone has an idea why it wouldn't, you know.
By the way, I wanted to ask, after you write the absolute x, why did we pick the negative one? Is that because we're going to...
Because we're going to negative infinity. So the x is going to be negative.
Yeah.
Right?
Thank you.
I mean, maybe a better way to see is that the absolute value of x, because that even me saying that, I'm like, well, that doesn't sound quite right. But the absolute value of x is defined as x if x is greater than 0, right? And negative x if x is less than 0. So you'll see right away. We're doing this case, so the absolute value of x is equal to negative x. Okay, but yeah, unless there's any other questions or anything like this, that's it for today. It's 8 o'clock. That was our session. Tomorrow we will do some more. We'll do some finish chapter 4, chapter 6, and then once we're done all that, then I will start doing the practice exams and any other resources that we have for doing stuff. But yeah.
Could you go over the question that you just did? Yeah, I'm kind of confused.
67. So I'll go over this part because this is the part that actually gets the answer.
Okay.
So first of all, that's the question. I'm going to factor out an x squared from inside the square root and factor out an x from this bottom part, right? So that's what I get like that. Factor out the x squared and the x. Then I can pull that x squared out to the front because it's just multiplying, right? So that those roots work like that. And the square root of x squared, well, that's the absolute value of x, right? That's the absolute value of x. And so over here, well, then we have to decide which version of the absolute value of x are we going to use. Are we going to use x or negative x? And that all depends on what x value you're choosing. Right? So since we're going to negative infinity, x is going to be less than 0. So the absolute value of x is going to be negative x. Then we just can cancel the x's. And then just apply the limit like how I did up here. Right? So as this goes to infinity, this will go to 0. This will go to 0. So it'll just be negative root 4 over 1. Negative root 4 over 1, which is equal to 0 too.
Okay, so I get like everything else except for like the part where it's like when we decide which, like negative infinity or infinity. So how do we like decide
this absolute value thing?
Yeah, like then how you decided to go from like negative infinity.
Because
so,
because if x is we're pretty much saying we have some function, right? Some function. And we're going to negative infinity, right? They're going that way, all the way that way. So 100%, the x value is going to be negative, right? The x value is going to be less than 0. Right? And the absolute value of x is a piecewise function defined like this. If it's positive, it's equal to positive x if x is positive, and it's equal to negative x if x is negative.
Oh, okay.
So we can you can just replace it. Since we know x is going to be negative, right? X is going to be less than 0. We can replace it with negative x.
Oh, okay. So the negative infinity is just like we decided to do that, or like
the negative infinity. That's part of the question. The negative infinity.
That's part of the question. Oh,
that's
okay.
Part of the question.
Right. My bad. Okay.
Yeah, no, don't worry. Yeah. Here, I'll put that like that. Negative infinity. That's a negative infinity. Yeah.
I understand. Okay. Thank you.
Good. No problem. So yeah. So then that's all for today.
Okay, thank you.
Thank you, Adam.
No problem.
That was very helpful.
I'm happy.
Thanks, man.
Everybody have a good night. Everybody
You too.
You too.
See you guys.
Bye, good night.
Bye. Have a good night.